Hello everyone, I'm Luka Banovic, the product manager at IRNAS development company based in Slovenia. It's very good to be back to the TTN. We first met in 2018 when we talked about drone mapping solutions. The year after, we pursued LoRaWAN underwater applications, and in 2020 we started a long series of talks about how to make long-lasting IoT devices and make the most out of them in the long run. Today, we will be talking about the mission that we took on with Plant-e, where we were trying to answer the question whether is it possible to build an IoT system that can collect and transmit environmental sensor data, is fully autonomous, maintenance-free, and nature-powered. So welcome to the talk about plant-powered IoT, which unlocks hundreds of possibilities for agricultural and environmental applications.
Ladies and gentlemen, my name is Wim de Jager. I am the R&D manager at Plant-e from the Netherlands. And as you just heard, we joined forces this year with IRNAS in Slovenia to co-develop the plant-powered IoT system for agriculture. And with this slide, I would like to show you why and what that entails. So IoT for agriculture, that means we're monitoring soil moisture, weather data, nutrient loads, and phenochem data. Those are some examples. Soil moisture is of course important for any type of plants, but it's also a very important parameter. If you're looking at CO2 storage in the underground, as well as forestry data, for example, the soil moisture content is an indicator for how much fire danger there could be. Weather data is pretty obvious. Nutrient load is an important one, especially in agriculture, since precision agriculture is upcoming more and more. Usually, nutrients via fertilizers are overdosed in order to make sure there's always enough. And phenochem data is an interesting new development that analyzes pictures or analyzes specific types of colors that could be a parameter for how healthy your crop would be, and I will explain that a little bit later as well. Some of these systems are already currently on the market. If they're often solar powered or battery powered, which means that sometimes you have to perform maintenance or exchange the battery. And almost all these systems are, for the large part, installed above ground. And that's also immediately our problem statement, because all of these things that I just mentioned mean that there's labor costs involved, but also that it's susceptible to theft, of course, hard weather conditions, and vandalism. And we try to solve that with a plant-powered IoT system. The plant microbial fuel cell, and especially a tubular plant microbial fuel cell, is already on the market. We have commercialized it as a product as Plant-e. And we have it in different configurations, and in this specific configuration we're looking at a vertically placed tubular plant microbial fuel cell. With the plant microbial fuel cell, we integrate it into the soil in a vertical tube below the groundwater level, and we utilize organic matter, say the food for bacteria, that is always present in the soil under groundwater level. By inserting an electrode, we stimulate a very specific type of bacteria to convert this organic matter that is present and convert it into electricity. We do that at the anode side, send these released electrons to the harvester, in this case the sensor and the IoT transmission device, where then at the cathode we use oxygen down below in the plant microbial fuel cell again to be reduced and to produce water. So basically, our waste product is water, and at the same time, we're powering we're powering the IoT device. So in the end, here you can see what we, with the power that we produce, what we could do with that. So we're producing about 1.2 or 1.4 milliwatts for 1 meter tube, or 14 milliwatts per square meter plant surface, and that's more than enough energy for low power energy data collection and transmission systems such as camera traps, soil temperature and redox sensors, and at the same time the LoRaWAN transmission. And now I will name two examples of two partners that we are co-developing or that we would like to implement this IoT device in. This is in Indonesia, where palm oil plantations are restored to wetlands. And you see here on the left picture a water level sensor that is predominantly installed above ground, where they have to exchange the batteries, and the labor costs are very high, where we are proposing a completely autonomous IoT device that is powered by the energy available in the soil that you can hardly see, and you never have to replace any batteries. And in this picture you can see the analysis of a picture through a phenocam system. So on the top left you see the picture in the dashed square. You can see the part of the picture that's being analyzed. And here it's being analyzed for so-called grain ears, the part of the plant that you see in the bottom left picture. And on the right picture you see the analyzed picture and the data that is actually being sent, where you can see that the distinguishment is made between the ears, the rest of the plant, and bare soil. So it's in the picture is analyzed for photospectral data and is then a proxy for how your field is doing, what the crop yield could be, or what the general healthiness is of your field in general.
We have repeatedly seen that decisions based on real-life data lead to much more valid and relevant methods to solving real-life problems. For us as IoT device developers, this poses a question: how do we maximize the value of an IoT device? Firstly, we can work on increasing its lifespan, which goes hand in hand with minimizing its power consumption. We also have to think about future-proof architecture to make it sustainable over all the upgrades and infrastructure developments for the future. And lastly, we have to take care about minimal maintenance. Maintenance in remote areas costs way more than the device itself, and we all know that. So, minimizing the power consumption on the one hand can be done by, first, a good design, and second, by minimizing data sending, which is something we have talked about in the past. We have talked about moving the brain from the cloud onto the device by utilizing the on-edge machine learning. What we haven't talked about is using alternative energy sources that are available on-site and coupling them with the device's original energy source, which is typically a battery. When we are talking about agricultural and environmental applications, we are typically talking about a large number of devices deployed over a large geographical area. In such places, it's very painful to replace batteries, even if it's after 10 years. On top of that, there is a large capacity of nature power typically available that we are currently not using. So in this mission with Plant-e, we try to couple the primary device batteries with the PMFC to achieve power autonomous operation of an IoT device. Of course, there is a high level of expertise needed both on the IoT side as well as the plant power harvesting side, which made this collaboration so fruitful. As a pilot, we designed a plant-powered phenology sensor, which uses a PMFC as a power source, to which we've attached a LoRaWAN device with about 4 microamp average power consumption. We are reading data from a simple 10-channel color sensor, but we also have the power harvester monitoring module included, where we can have a look at storage element levels, primary battery levels, source levels, which gives us a degree of control over the power harvesting itself. What you see on the image here is the first plant power harvester. The way it is different to other power harvesters is that it is specifically designed to be coupled with a PMFC. The interaction between the harvester and the PMFC is very delicate, as if it's done wrong, it can damage the biofilm on the PMFC and make the power harvesting inefficient or even impossible. It includes automatic impedance matching, and it uses supercaps as the main energy storage element, backed by an alkaline primary battery. In this case, we are supplying 2.5 volts at the output, to which we have hooked a LoRaWAN device, and as a power input we are using a PMFC supplying about 600 millivolt power. What we have managed to prove with this design was that the PMFC is a strong enough power source that we can use the power it generates to power an IoT device. Secondly, we have proven that it is possible to develop a power harvester that is specifically tuned to be coupled with a PMFC. Thirdly, we have proven that we can attach a low-power sensor node to the system and run it over a longer period of time, which closes the loop on all important components of such a system. All this together makes our pilot run very successful, and we are very pleased with it. The next step we are trying to take is to demonstrate this on a larger project with up to 100 sensors deployed on a single site. Next, we would like to validate the universality of such a design by applying multiple parallel pilot deployments in different areas of the world. Lastly, we would like to launch a production-ready design that can be used in various agricultural and environmental IoT applications. Hopefully, we have unlocked some ideas today with talking about plant power harvesting in agricultural and environmental IoT, and we are very keen to hear your thoughts and comments. Thank you for your attention.